So thanks again for the organizer for inviting me. That said, when I'm looking at the audience, I'm pretty sure that the content of my slides will be familiar for many of you, because you might even be more expert than I am on many of these topics. But still, this talk is going to be more addressed, I would say, to people who are starting or in the middle of their journey to let's say going from tier 2 to tier 0 and to Exascale, to use Exascale resources. So I work at Cenaero, which is a research center dedicated to numerical simulation, and we also operate one of the 2 tier 1 supercomputers in Belgium. And I personally contribute to the development of HPC workflow applied to CFD application. So I will just introduce the concept of the tier concept. You have already seen this pyramid if you attended Stefan talk a few minutes ago. So we basically classify the supercomputers in Europe in 3 categories. You have the tier 0, which are the biggest systems available in Europe. So these are of Exascale class and leadership HPC. So they are managed by EuroHPC. And currently we have about 10 systems, yeah, right here. So we have Jupiter, which is the only Exascale system so far. Then we have 3 pre-Exascale systems, including LUMI. And then we have a mid-range petascale system spread over Europe. And there have already been some slides earlier today that showed these supercomputers. At a second level, at the tier 1 level, which include basically Lucia and soon Sophia for the VSC, you have petascale class systems that are managed at the national or regional level, I should say here, and are usually 10 to 100 times smaller than the tier 0. And then at the lower level, you have the tier 2 supercomputer, and basically almost all universities in Belgium have such a system for the user. So now the question is, when is it time to request an allocation on a bigger system? When is it time for your application to jump to a bigger fishbowl? So, well, the first reason is when your computation takes too much time, because the science that you are trying to address is too big. It takes too much time on your smaller system to be solved, or your problem is so big that it doesn't even fit anymore in the memory of your system. So that's a good sign that you need to go to a bigger system. And for this, you have preparatory access to larger systems, which is extremely essential. You really need to take this opportunity to test your code and identify bottleneck later that you will encounter later. So for production simulation, the access is granted based on a project proposal. So on the tier 1, I will talk about Lucia because I'm more familiar with it. Academia can address their proposal to CC. You just need to be a member of one of the Walloon University. And research centers and industry can address directly their proposal to Cenaero and will handle them. For tier 0, well, Stefan already introduced that a couple of hours ago, but you have the EuroHPC regular calls, so I put the link here. These are highly competitive proposals, so you need your code to be extremely ready, and you have to demonstrate that in your proposal. And then you have also the, and of course this allows you to access all the supercomputers available in Europe. And here in Belgium, I think we have quite lucky to have access to the LUMI-BE share, because Belgium is the second contributor to the LUMI consortium. And based on this, well, you have to know that 50% of the compute time on LUMI is distributed through EuroHPC regular calls, so these guys here. And the other 50% is distributed among the participating countries of the consortium according to their contribution. So that means that we have access to 7.4% of the total compute time on LUMI. So this is an extreme privilege, in my opinion. But with this privilege come also big duties and big responsibilities. And so it's our responsibility first to use these resources queries as efficiently as possible, and also to produce meaningful and impactful science from these resources. So here is the link if you're interested in applying, and there is all the details about the proposal requested are mentioned in the ENCC Belgium website. I'm not going to go through too much about the details on this slide because Stefan presented some of these information, but basically if you are interested in going to LUMI, you have the preparatory call. So you get for this a small amount of resources just to port your code, optimize, identify bottleneck, benchmark. So you don't do any production of science there. It's usually a small duration. And for the LUMI-BE regular calls, there are 3 per year. So one will be in March, the next one is March, and so you get medium size allocation that basically stand between, stand a little bit lower than what you can get from EuroHPC regular call. For the regular call, you get 2 calls per year, usually in March and September as well, and this is for a single year. So what is expected in this proposal? Well, first you have to, at least for the LUMI-BE regular access, you need to describe first your research, what you are going to do with these resources, and then you have to demonstrate technical readiness with real benchmark. You have to show as well the scalability of your system, how efficiently you are going to use the resources, and you have also to justify the resources that you are going to request in terms of CPU or GPU hours. For the EuroHPC regular call, it's pretty similar, except that you have a really strong scientific review on top of what you get for the LUMI-BE call. So now I would like to share with you some of the necessary components or ingredients or bottlenecks, at least, that I've been working on or I've encountered during my journey to, well, not yet exascale, but at least, let's say, to petascale simulation. So first, obviously, you need a scalable solver. So I'm not going to provide all the key ingredients for a scalable solver because you know your code much better than I do. But usually, good advices or good advices include to hide peer-to-peer communication with computations and also profile the code to identify performance bottlenecks. And I would also again share the advice from Kurt, who said if you're interested in going to EuroHPC systems, please, and if you have bottlenecks, identified bottlenecks, please go and see them so that we can maybe organize a Belgian hackathon with the LUMI guys. So that's something interesting to share as well. A second, well, having a scalable solver is fun to work on, but this is not what is going to guarantee a scalable simulation. You need also to pay attention to the load balance of your code, and usually this is handled during the pre-processing. So I'm more familiar with domain decomposition approach, like finite element methods or finite volume methods. So these are based on the decomposition of your domain represented by a mesh in some mesh partitions. So that I'm going mainly to focus on this kind of decomposition. I/O is usually overlooked, and this is one of the biggest bottleneck in terms of scalability. So I worked also a bit of that, and I'm going to share some experience in that. Post-processing and in-situ analysis are also key ingredients. GPU, you cannot go to Exascale without GPU right now, so this is almost, well, this is a requirement right now. Portability, because there are several GPUs going on, available or different systems, so portability is also important. And of course, you need a robust hardware and system software, but this is out of my scope. So load balancing. Well, this is essential, as I mentioned, if you want to reduce the waiting time in peer-to-peer communication and global communication. If one of your rank has more job to do or more work to do than the others, at some point the others will have to wait for this rank to be available again and finalize the communication. So this is essential. I've seen codes that scale very well and sometimes stop scaling, and the reason is because one single part is enough, or mesh part or single rank is enough to ruin completely your scalability. So for domain decomposition approaches, we usually work with Metis. You have already heard about this library earlier today. And it's usually good at balancing elements but not necessarily the other mesh entities like faces, like edges or vertices. And your code, or the performance of your code, may also depend on these lower order entities. And so I'm going to talk about two codes in the future. The first one is a code that is being developed at Cenaero called Fidelio. It's an explicit discontinuous Galerkin method, so designed to solve for flow simulation on GPUs. So this particular code is based on ghost elements for the mesh partitions, and that means that the cost of volume integrals will be proportional to the number of elements, so usually easy to balance, but the cost of the flux evaluation, and I encourage you to see again Orient's presentation, who did a nice work to explain how it works. The flux will be, the cost of the flux will be proportional to the number of faces or interfaces between elements. So it's important to balance both of these entities, and usually you get only one. Or there is a risk that you only get one. And I'm also going to present a code that I worked on during my postdoc a couple of years ago, which is a FASTA developed at the University of Colorado. So this time it is an implicit massively parallel pure MPI finite element flow solver, and the domain, the mesh partitioning is based this time on duplicate vertices. So if you take here a mesh and you partition it, basically you don't have ghost cells, but you have duplicate vertices on the part boundaries. So the cost of the linear system assembly is again going to be proportional to the number of elements. Good. But the cost of the linear system is going to be proportional to the number of vertices, because here you have a GMRS or a linear system to solve, and we use GMRS in this case. So we studied the scalability of this flow solver FASTA with a flow control application. It was at that time in 2000, the simulation were run in 2015, but the publication was in 2018 for this scalability study. So we had like 1 billion cell on an anisotropic mesh. So this is a very complex geometry with cavities, etc. So while the mesh partitioner has a difficult job to produce nicely shaped partitions. And we went from 8,000 partitions up to 1 million partitions on the BlueGenQ system at Argonne at that time. And as you can see in this plot, this represents some the vertex imbalance per part. So you can see that most of them will be around 1, but you have a few spikes in red, and basically this guy or this guy will dominate the scalability of your, or the lack of scalability of your simulation. And so there is a library, we worked with a library called Parma at that time, which was able to basically reduce all the imbalance of these few parts while maintaining still the imbalance of the mesh elements. So you can see how the imbalance in terms of element evolve as the number of partitions increases. So it's still okay. I would say 12% imbalance in terms of elements is not bad, but when you look at the vertices, it can go to almost, well, 90% in this particular case. So if you have one part that has 90% more vertices to deal with, you will have to wait. The other ranks will have to wait for this guy. And with this library, you can see that we were able to retrieve about almost a perfect imbalance in terms of mesh elements and mesh vertices. So that was for extreme scale, like 1 million mesh parts is not going to be useful right now because of the advent of GPU. So the GPU relieves the pressure on mesh partitioning in balance, but still we still need to keep an eye on low order entities, because with GPU you could still end up with some imbalance in this region here. So that was for imbalance. The next topic I want to address is input and output, so I/O. And basically I/O is needed for every application. For checkpointing, because you want to run a long simulation and 48 hours is not enough, so you need to restart. You need to be able to restart. And of course we don't run simulation just for scalable scaling plots. We want to learn something, extract physics insights from this simulation. So post-processing and data analysis is also critical, well, it depends critically on I/O as well. And usually nobody likes really to work on I/O, so it is being overlooked. And the question is really how to transfer data efficiently from thousands of nodes to physical disk, and also at some point to reload them for your post-processing or data analysis. And the need for your simulation running on thousands of nodes might be different in terms of I/O than your post-processing. And I will highlight that in a second. Golden rule, most parallel file systems don't like small files or large amount of small files. I think Kurt agree with that. Everybody who has been working on supercomputers knows that. So without parallelization, without collective I/O, I/O will become a bottleneck for every application. So you can rely on MPI I/O, which is part of the MPI standard, for your own, I would say, format. Or you can also rely on other high-level libraries like HDF5. But the question is at the end, don't forget to ask yourself the question, who will consume the data and how? Especially for visualization tools like ParaView, which is a ParaView user, so I'm going to talk about it in a second. So the key here is to plan the whole data workflow when you develop your code. And so this is usually the naive approach that we all usually start when we develop a code. So it's basically to write one file per MPI rank. So that's something that we should not do, because as n increases, we'll end up with thousands of small files. You will end up also with bottlenecks in the metadata server, and actually you will at some point crash the file system and get an email or a phone call from your IT department. I did it, so I know. Also, having thousands of small files is very difficult to manage at the end. You have, well, to transfer or to just list this file is very difficult. So a better approach is to use, let's, for instance, MPI/IO, which will allow all these ranks to write simultaneously and collectively in a single share file. And so this is going to be much faster this approach is going to be much faster compared to this one, because behind the hood, the file system, the file system server will split your file and will redirect a portion of your files in different disks, and so it's going to be much faster in this way. And then at the end you have a big giant file, so it's easy to handle. So, end of the story? Not exactly, because you have also to think about your visualization and your analysis. And usually your visualization or your analysis will maybe run in serial, but with such large data it will probably run in parallel as well, but on a lower number of ranks. So I would say, let's say M ranks with M, one or two order of magnitudes smaller than N. So typically M will be, for a ParaView server, will be around 10, 20 ranks of ParaView. And unfortunately for ParaView, and I think this is the case for most visualization tools, there is no collective I/O. So each rank will try to access its data independently from the other ranks. So reading thousands of files, of small files, is still slow. Well, it's slow, but can still work in some circumstances. On the opposite, if you ask a ParaView server to read a single shared file with several ranks accessing this file independently, you will just end up with I/O contention, and that's going to take really hours. I tried that as well. So a good solution, or a good, I would say, intermediate solution, or a good compromise is to use, for this kind of application, a CFD application, is to use M files shared between N processes. So you end up with N large files, which is still manageable, and each of these files will be then read by your visualization tool like ParaView in an independent way, but still with a low number of ranks that's still manageable. So even if we have, I would say, improved in some sense the way to write checkpoints and data to disk, the I/O performance is not keeping pace with the increasing compute power, clearly. So writing to disk is slow and will be even slower compared to the pace at which you are generating your data. So here I'm representing a typical workflow where you have a simulation running in parallel on your computer, your supercomputer. You write your raw data, your binary data to the file system, and then later you load them again in a visualization cluster with ParaView, for instance, running in parallel. So you have a ParaView server here that is connected to a ParaView client and this is you sitting with your laptop at your home institution. So this transfer here is very fast because you are just transferring pixels from your ParaView server to your laptop. But again, writing data here is slow, and loading them here is slow as well. So for large amount of data, if you are, for instance, dealing with a transient phenomenon that you are interested in studying, it's not going to work because you cannot save thousands of time steps to the file system and loading them to produce a movie, for instance, as the nice one we have already seen earlier today. So a better solution is to couple your simulation to an analysis or visualization library like Catalyst. This is the onboard ParaView library in some sense. And then you can run your simulation and your analysis concurrently with the simulation. And you can, and for instance, here I'm representing a batch in situ visualization chain where your simulation will produce pixel and will write directly pixel, so light files, to your file system that you can then use to produce, for instance, a movie. So this is going to be much faster to do this than saving all the raw data as I showed. And I'm showing an example here. This is a turbine flow simulation, the T161, that was run at Barcelona several years ago. It was even before LUMI, I think. And as you can see, we are saving all the PNGs at a very high frequency allows to make a very detailed movie, and that allows us to study the transient flow or here these instantaneous field. Here we are looking at the strong vortices, horseshoe vortices that starts at the intersection between the end walls and the turbine blades that you see here. We can also analyze I appreciate here the transition of the flow, and this movie would not have been possible to generate without in situ visualization capabilities. So this is really critical. It's not just to make some nice movies, it's also to learn about the physics of your unsteady phenomena. All right, next step, the advent of GPU. 5 minutes already, wow. That's going to be hard. So if you look at the top 20 supercomputers, basically there is only one that is still based on CPU. All others are based on GPU for a simple reason: they have a better flop per watt ratio. So if you look at the best ARM CPU, you get 16 gigaflops per watt, whereas the Green Top 500 gives you like 60 or 70 gigaflops per watt. So there is a factor 4 between the best GPU and the best CPU. And if you look at LUMI-G compared to LUMI-C, this factor increases even further. You have a 10x between the two. So in other words, resources are much better used if you have a GPU code than if you have a CPU code. And that's the reason why Lucia is made of, the computational power of Lucia is made of 60% of GPUs, and on LUMI it's even further, it's 88%. So if you stick to a CPU code, you can use only 2% of the resource available on LUMI. So this is a bit sad. What is the difficulty or the change of paradigm between CPU and GPU? Well, if you compare a CPU node with one of the GPU on Lucia, basically your R-peak increased by a factor 4, your bandwidth increased by a factor 4, so your arithmetic intensity is basically preserved, but you have way less memory available per node. So this is really the key. So if you like implicit methods in CFD, for instance, it's very hard to handle with, to live with that. You probably have to go back to explicit methods. So I would like to introduce here some GPU porting initiatives here in Wallonia that are funded by a FEDER project named Virtual Lab, and because again there's a necessity to port our code to GPU. So Orion has already introduced his GPU solver GMesh DG for Maxwell equation. Louvain and Philippe Chatelain, who is also here, is developing a multiphysics HPC platform called Murphy for the resolution of PDEs in general. And at Cenaero, we have also started to work on the development of a multi-GPU flow solver called Fidelio, as I mentioned. And you can here see the first weak scaling plots that we have produced so far, up to 128 cores, GPUs, and the next step will be to scale up this further on LUMI. Also a difference in terms of paradigm between the GPU and the CPU. Well, we need to saturate the GPU to extract as much performance as possible. So here I'm showing the number of degrees of freedom we can treat per second with respect to the mesh size, and you can see that we really need to feed the beast. I would say that's the picture that represents this. You need to give enough data to crunch to the GPU to reach the performance. So that's why I showed some weak scaling plots before, because we know that we need to stay in this area here to get the best performance. And that's the same on Lucia on the left, and as well on the same on LUMI on the right. I don't resist to show another nice picture, a nice movie that we've been able to generate. See, this is the first industrial application of our CFD code Fidelio, where we study here a compressor blade. So this is a blade that you encountered in turbo machinery, so aircraft engine. And we are studying here a novel design where we have, instead of having one single blade, we study two blades that are close together, which have nice properties in terms of operating range. So I don't have the time to go through that. In terms of good practice, it's nice to profile your code. It's a necessity also to profile your code to identify bottlenecks. So I'm listing here a few tools that can be useful. You have, well, first, traditional wall clock timers that can provide you, for instance, this kind of plots here. This is on LUMI-BE, and I wanted to highlight also the spikes that you can see here. So this is the time taken for each time steps. And you can see that here I have sometimes some spikes. So despite the fact that I'm using MPI-IO, you can see that I/O is still slow and will remain slow forever. You have also nice profiling tools that can help you on NVIDIA hardware. You have Nsight, you have Rock Profiler, VTune for Intel, so different tools available for this. I would like also to mention some training opportunities to learn more about it. There are many, many opportunities. The first one, I advise you to subscribe to the mailing list, the EuroHPC mailing list, where all these trainings will be listed every month. So Benoit is taking care of that. You have also training opportunities organized by CC and VSC, and basically most of the big supercomputer center also organize their own trainings. Which brings me to the conclusion. I had to rush a little bit at the end, but I think I'm still 1 minute comfortable. So, as a conclusion, the tier 0 system can provide massive compute capability, but we need to be ready to use them. And for this, the whole workflow needs to be scalable. Not only the core of the simulation of your code, but also the pre-processing and the post-processing, I/O, etc. So moving from tier 2 to tier 1 to tier 0 is not simply increasing the number of cores. You will encounter probably some bottlenecks, known or sometimes even unknown. So I/O is one of them. Communication and load imbalance can also become an issue. You need to make sure that if you're working with GPUs, you keep feeding the GPU, because it needs to crunch data as much as possible. And you also need to pay attention to data movement. I have no time to go through that, but it's also important. So you need to basically pay attention to scalable algorithm, compute, communication, I/O, as I mentioned. And you also need to use the appropriate programming models, MPI plus anything for your accelerators. And that's sometimes a difficult choice. You have OpenACC, you have CUDA, you have HIP. And the main issue is that you need to ensure portability of your code. We currently, as a researcher attached to a Belgian entity, we have access to NVIDIA hardware, like Lucia and Sophia, but also to AMD hardware in LUMI. So we need to be able to use both efficiently. And I will conclude on that, and thank you for your attention.